Welcome everyone. My name is Manva and I would like to introduce the first speaker of the day. That's Professor Umakant Rapol. So he did his bachelor's from Solapur and master's from Pune in the University of Pune, and his physics later on from IISc Bangalore. And he's worked for a long time outside India also, and since 2009 he's a professor here. So he's a professor of physics, and as you can see he works in atomic physics and quantum optics lab. Now have all of you have heard the word quantum? Okay, what does quantum mean? You've heard the word, but then what does it mean?
It's like the science of people. Something which is on a
very small scale? Yes, you're right. So we are talking about not just atoms, but things which are even smaller, way smaller than atoms, subatomic particles and so on. Now you can imagine if you are talking about something that is so small and you want to do experiments with something so small, of course you need to have sophisticated instruments for that. So Umakant sir does some amazing experiments at that scale, at that level of size as well as, time. So he's going to talk about what kind of experiments he does, and as Arnab also mentioned, you have to do this in collaboration with a lot of other people because no single person can do everything in science. So he also collaborates with a lot of people from IISER as well as some scientists from IUCAA. So he's going to take us on this journey of his quantum optics lab and what kind of work he does and the applications which are there of all the quantum things that he works on. Okay, thank you.
Thank you very much for the kind introduction. First of all, I'd like to thank the organizers for giving me an opportunity to speak to young minds here. And the task in front of me is a very difficult one because the topic that has been given to me based upon what I do, it is very difficult for even seasoned researchers to understand, and that's about the physics of quantum mechanics and quantum physics. So today I'll try to make my best efforts to impress upon you how quantum mechanics can be harnessed for building very useful and very state-of-the-art and even very futuristic devices. And yeah, I mean, just run you through some of the examples and how quantum mechanics can be used for building these. Now, before we delve into quantum technology, we should first start with classical mechanics, okay? How many of you have heard about quantum mechanics? How many of you know about wave-particle duality? Some of you, right? Okay, fine. So, as you know, quantum mechanics was invented in the early 1900s, okay? I mean, something around 1905, 1910 or so. And it started off because there have been very interesting phenomena which became difficult to explain using simple classical physics. When I say classical physics is all what you learn up to school and so on, and what you see in nature, everything as a child when you see and navigate through the process of understanding different phenomena, you kind of get some intuition about how things behave, how things move, and how things evolve and things like that. And more often, the dynamics or the motion of particles, objects, sun, moon, all these can be to some extent explained by simple Newton's laws of motion, okay? So, but going beyond that, there are obviously more complex formalisms above Newton's laws of motion to explain very complex dynamics of, say, planets and Earth and even air molecules and so on. But all this... Yeah. So all these kind of hit a wall up at certain point. For example, the way quantum mechanics was invented was when people started to understand, started to look into how different materials, different atoms, different molecules, when they emit light, and when you look at what kind of light these atoms emit, then one started seeing. So when you look at light, sunlight, say, you see that when you put it through a prism, you see a broad gamut of colors, right? I mean, or a broad spectrum of different colors. Now, to just put it in a more representable manner, how the intensity looks like, this is the wavelength, okay? On the x-axis. And then if you plot the intensity for different wavelengths, you would see something like that. I mean, at different colors, the intensity is different. Okay? And then it peaks at certain value. Now, this is the kind of behavior the light exhibits when you represent its intensity as a function of the wavelength of what light it is emitting. Now, this is the light coming from sunlight, okay? Now, there is a very peculiar nature of objects like sun when they emit light. So, it behaves like this. It falls, or it increases, and then it peaks at some maximum wavelength, and then it falls off. Now, if you take a iron rod and start heating it on a gas stove, right? So it first becomes red, and then if you heat it further, it might become yellow, and then it turns blue. What is happening is that the prominent color that an object emits when it's heated is at this peak wavelength, and then this thing keeps shifting to lower and lower wavelengths as you keep increasing the temperature or of that object. Now, this behavior was a very puzzling behavior in 1900s, okay? When they tried to explain this intensity, see, because of scientific inquisitiveness, it's not just looking at a rod and then seeing how the color is changing, right? You have to do a detailed analysis of how this plot, how intensity of different wavelengths that particular object is emitting. And then when people did this, they could not explain this behavior using standard classical mechanics. And that's where the birth of quantum mechanics took place. Now, what quantum mechanics said was that the energy that is emitted by all these, the constituents of this, say, iron rod, or they say the sun, which the constituents within these, like atoms or molecules, which are vibrating around their mean positions, and they are actually emitting this energy out in form of light. Now, that they were unable to explain with classical mechanics. Now, what the revolutionary idea that came up was by Planck, who said that, okay, this light that is emitted in packets, okay, in packets of, which is, this energy is proportional to the frequency of that light. This is frequency, okay. Now, the proportionality constant, now we call this as the Planck's constant. So this was a very revolutionary idea which came out in terms of quantizing energy that is emitted by objects. Right? So this was the first, the birth of quantum mechanics. Now this progressed to a large extent, and it went to the point very rapidly in telling us that when light is emitted by atoms themselves, that is not emitted in this continuous fashion that I mentioned, right? So we see the hydrogen atom. So there is one electron and one proton, and this electron, the classical picture is that this electron keeps rotating around this nucleus, right? Now, the light that is emitted from this atom, when this atom is excited by electrical discharge or heated or by collisions or something, what happens is that this electron goes to higher orbits and then it comes back to lower orbits. When it comes back to lower orbit, it emits light. Now, people initially could not explain why this emitted light, when I plot this light, it has sharp peaks at certain wavelengths. This is lambda, this is intensity. this is not a continuous thing like a hot body, right? It is something that's emitted in very specific small bands. Now, this could be explained only by the principle, by extending the concept of quantization of energy, and this quantum mechanics progressed further very rapidly with this. And it was said that not only is energy quantized, but also these particles that we call, right, electrons or any object, it is not just a point particle, okay? There is some fuzziness associated with this particle. So when you go at an atomic scale or at the scale of the size of electrons, these electrons are not just a point particle. They have a fuzziness associated with that. And that concept was called as intelligence. So de Broglie, a French physicist, came up with this concept of wave-particle duality. So particles and waves, they behave interchangeably depending on the circumstance. Okay. Now, using this wave-particle duality, and there is a lot of mathematical formalism that goes into all this, what I am saying, but I am just trying to give you a feel about the advent of this invention of quantum mechanics. Now, when you associate a fuzziness to this object, now this electron, when it is, if this electron is taken not as just a point, but this wave, okay? So what happens is that this wave is going to close onto itself. It's like a wave which is closed onto itself. Now, if I take a string, tie it to the two walls here, and then I strike this string, there are going to be waves that are going to propagate, right? Now, but what happens is that at the end, the wave has to have the amplitude of the string has to be 0 at the points where you tied it, right? So the walls are setting up a boundary condition. Now, same thing if you loop the string into a ring and then strike a wave into that, it's going to basically these vibrations are going to form in such a manner that it has to satisfy the condition of certain integer wavelengths that have to be covered within the circle that the string encloses, right? Same thing happens here. So electrons are forced to stay only in certain orbits where the wave closes onto itself. So it basically gives rise to discrete orbits, not continuous orbits. Now, in each of these orbits, this wave or the electron is carrying certain energy. So higher the orbit size, the energy is greater than the previous one. Now, when this electron goes from one orbit to the other, that excess energy, the energy difference between these two, is emitted as light. And light, again, it can be treated as either a particle or a wave, depending on the circumstance, depending on the kind of experiment, depending on the kind of situation the light goes through. So that is this wave-particle duality, and this is called as quantization of energy levels. Now, another beautiful thing that exists in quantum mechanics is that the first thing that I wrote there, superposition. Now, yeah.
Jimmy probably got higher levels in the board, then the excess effect could probably be get away. But they can both from the
You have to give that much energy.
they will need that much.
Exactly that much energy.
So
They absorb. So if I send in light of exactly that, the difference energy, then the electron will get excited to the higher orbit.
God, you did.
Now, let's take a scenario. Let's take a classical picture. I'll not draw waves here now. So this is electron orbiting in one orbit. Now, if I take another situation where the electron is in the outer orbit. Now, And the state of this electron in different orbits can be described in a very formal manner with a lot of mathematics in terms of wave functions and whatnot. And the state is defined as the quantum state of that electron in that orbit. Now, this interesting feature, superposition, that I mentioned here is the following. Electron can not only exist in either orbit number 2 or orbit number 1, but it can also exist either in 1 or 2. So if I create a state, it's called a superposition state, which means it's a mixture of state 1 and state 2. Okay. Now, when I create such a mixture of state, and it is possible to create that experimentally, if I create a state, say, 0.5 times this one plus 0.5 times 2, every time I look at this atom to see where my electron is, 50% of the time I get an answer that it is in state 1. 50% of the time I get an answer that it is in state 2. You can also create a state where 25% of the time it's in 1 and 75% of the time it's in 2. So this is called as a superposition. So this can only happen at the level of atomic scale, where the states of these electrons or whatever atoms is defined, is governed by the principles of quantum mechanics, and that's what it is at an atomic scale. And all these effects, they come into picture to define the properties of any materials and their behavior at a macroscopic scale. Now, the other feature is this entanglement. This entanglement is a very complex phenomenon. So, I think I'll try my best to explain. So, for example, I take a ball which is half white and half black. Okay, I spin it randomly and then throw at you. When you hold it, you will either, when you hold it and see, you might see white or black facing your side. This is probabilistic. 50% of the time it can be, you can see it as white or black. I take two balls, I randomly spin them and throw it at two people. Each one of them will see it either black or white, or both white, both black. There won't be any connection as to between the the results of the two people, right? One person might see white, but he cannot say whether the other person has seen black or white. They are completely independent random events. This is in classical mechanics. Even in quantum mechanics, yes. Now, if I do some magic in my hands when I'm spinning these balls, what happens is that each person 50% of the times might see white or black. Okay? But now what will happen is that independently they are completely random. But by looking at what I see, white or black, depending on how I do that magic in the beginning, I can say with a high degree of confidence about what the outcome of the other person is, whether he will see white or black. I can do this magic initially in such a manner that both, if one person sees white, the other person, he can say that the other person will see white definitely, or vice versa, or opposite. Now, this magic that happens, that can happen only at a quantum mechanical, in quantum mechanics. And this magic, whatever happens between the two particles, it's called entanglement. And that is a very, very important resource in quantum mechanics, which plays a very big role in defining a lot of properties of these atomic and subatomic particles at a macroscopic level. Now,
So I think there's a question.
yeah.
So I just had one question. relating to the superconduction mass of the molecule there. So does the electron have to exist in the circumference of the ring that you want to go inside and
Inside meaning?
like inside it?
Here.
Driver. Can it go?
Here. No, it cannot. So these rings,
Yeah.
each of this orbit has certain angular momentum. And this angular momentum has to be integer multiples of Planck's constant. So it is, the orbits are quantized. So these are, this is a model that was given by Niels Bohr. It's called the Bohr's atom model. Okay. Okay, so I told you about the wave-particle duality, I told you about superpositions, I told you about entanglement. The fourth thing that I didn't tell you yet is about tunneling. Tunneling is again a very interesting phenomenon of quantum mechanics, which can happen at only subatomic scales, and this is not something hypothetical. These phenomena are used in day-to-day devices, okay? So there are, before I tell you which devices, I'll first explain to you what tunneling is. I take a cricket ball, I throw it at the wall, what happens? It bounces back. Now, I take a quantum particle, I have some hypothetical wall, I throw it at that wall. Not all the time the particle will bounce back. There are certain times, or there is a probability that the particle can actually go through the wall and be seen on the other side. Now, it depends on how strong the wall is. So, what it means is that in physics terms, this is a potential. There is a potential barrier. This is 0 and say this is infinite, very tall. Say I come with this electron, okay? I put it here. Now this is not just a particle, it's a wave. If this is infinitely tall potential or a thick, very strong wall, this wave reflects back. But if I keep making it smaller and smaller and shorter, what happens is that some of it goes out and the wave goes out of the wall. What it essentially means is there is a certain amount of probability by which you can actually spot that particle beyond that wall. Now this is called quantum mechanical tunneling. And this phenomenon of tunneling led to at least 3 Nobel Prizes in the history of physics Nobel Prizes. And one example of that is a semiconductor diode, which is called as a tunnel diode. It's also named after a Japanese scientist Isaki. It's called an Isaki diode. And these diodes are used for generating very high frequency electromagnetic waves in the range of several gigahertz. And those diodes rely upon this phenomenon of the tunneling, and it's quantum mechanical tunneling. And there are other devices which also rely upon this quantum mechanical tunneling, and they are called Josephson junctions. I will not tell you more about it. You go and look up what these are. But these are things that completely work on basic quantum mechanical principles. All this what I told you. Okay, so what is this quantum technology? Okay, now I'll switch gears. So all this development of quantum mechanics, everything started in early 1900, and then it developed into becoming more and more sophisticated and trying to explain a lot of phenomena, trying to predict new particles that can exist in nature. And you must have all heard about Higgs boson and things like that, right? So all this as things started developing, most of the times, all of these, you did not have control over what was going on in terms of all these properties, 4 properties that I told you about quantum mechanics, how they were working at an atomic scale, and they manifested themselves, or they manifest themselves into some properties of the material at a microscopic level in a classical world, which we can see. right? Like, for example, say mercury. At room temperature, it is liquid, it is a conductor of electricity and all that. You keep cooling it down below a certain temperature, say at below 4 Kelvin temperature, 4 Kelvin absolute temperature, which is just minus 270 Kelvin or so, it starts becoming superconductor. You know what superconductors are, right? And how if you pass current will flow through it without any resistance, zero resistance. And if you take a wire, a superconducting wire loop, and you put a current in that wire, that current will flow in that wire forever. Okay, this is how MRI machines work. So there is a big superconducting coil inside which is generating magnetic field, and this current is passed through the superconductor, and this current flows forever, and it's called persistent current, and you generate this magnetic field. Now, this property, what happens from room temperature to when you go below 4 Kelvin, how the superconductivity is formed, is all this property is macroscopic property, but at an atomic level, there are a lot of things happening in the material, all the superpositions, entanglement, tunneling, all these things are going on in a very complex fashion, which is leading to formation of a superconductor, right? So now we don't have any control on how this mercury should behave. There are many examples of other superconductors also, niobium, etc. The point is, you don't have any control on how to engineer these properties at a microscopic level, at an atomic level, so that my superconductor now will start becoming a superconductor at, say, ice temperature. We don't know what happens inside, and we don't have much control on that. People are trying to understand. So all this is called as a first quantum revolution, the entire thing that has happened last century. Now we are entering into what is called as a second quantum revolution, where we are trying to harness these four properties in a manner where we can control those at an atomic scale, or when I say atomic scale, you just think of it as I am referring in general terms to scales at where quantum mechanics start playing a role, okay? So using these properties, by tailoring, by engineering these properties, one has opened up the enormous possibilities in achieving these things which I have listed out here.
Yeah.
To build computers, for example, which are so fast that classical computers that we see, big supercomputer clusters and everything, they cannot do certain jobs in physically realizable time scales, okay? But it is projected that quantum computers, when you use the principles of quantum mechanics, they can work much, much faster. You can transmit information without actually getting eavesdropped. So you can transmit information from one point to the other point without losing the secrecy of the information that is transferred from one point to the other point. You can make sensors. There are many sensors, things like detecting light, detecting magnetic field, detecting Earth's gravitational field, gravitational acceleration, rotations, and many more things. Magnetic fields, electric fields, etc. You can make those sensors like with many thousands or million times better in sensitivity than existing sensors which just rely upon classical principles. So as I said, some of these sensors, like acceleration and rotation sensors, they can be used for navigation system, for navigating certain objects, like for example missiles, aircrafts and submarines, etc., where in deep space when these objects fly, you don't have any GPS there, okay? GPS is only on Earth. It is because you have a constellation of satellites around the Earth which are sending the signals everywhere on the Earth, and your mobile device or a navigation device is measuring the time of arrivals of these different satellites, and it will tell you where I am by doing some mathematics, by doing triangulation and all that. But if you are in deep space, you don't have any satellites which will tell you where you are. The only way you can find out where you are is you should know where you started off from and then you should measure how you are accelerating, which way you are rotating every point. It's like somebody blindfolded, and if I ask the person to navigate through this, then when he starts walking, he will first see how far he has gone straight, and then at some point he has to turn, he or she, and then he has to move some distance and then again rotate. All this he has to do mental calculations about his motion. To get information to do that, you need this navigation device, sensors, which tell you accelerations and rotations. So one can make better devices using this. Okay. So I'll give you a glimpse about computing first. How do classical computers, our standard computers, work? Inside, if you go in the central processing unit, it has what are called as gates. Inside the computer, inside the processing unit, there are things which do lot of arithmetic, okay? Multiplication, subtraction, addition, division, all that. But if you go even deeper, there are things what are called as gates. And based upon these gates, there are many subsystems that are built with these gates. And then they work as your blocks which will store information. In this case, in classical computers, the information is basically a stream of zeros and ones. What are these zeros and ones? These are basically some state of a voltage, okay? Either it is 0 volts or some 5 volts or something, depending upon what kind of logic family is used. Now, the zeros and ones essentially are basically, even if you go even deeper into see these gates, for example, it's nothing but some transistor inside. It is either on or off. If it is off, the voltage is 0. If it is if it is off, the voltage is 1. If it is on, the voltage is 0. So this is how all the information that we put into the computer, the data that we put into the computer, it's converted into these logical zeros and ones and stored inside. And these voltage level zeros and ones are all processed using these gates and flip-flops and whatnot. So this is, for example, what is called as a flip-flop. This is a basic building block for memory, classical memory. Now, same thing. Now, in this case, where you have this classical bit, the values are only 0 and 1. Now, imagine if I had used that electron in an atom example. Yes. The state of the electron would be either lower state or upper state. Lower state you can label it as 0, upper state you can label it as 1. Either it's in 0 or 1. But remember the principle of superposition that I told you, right? It can be in either lower state or upper state, either 0 or 1 with certain probability, 50-50, 25-75, and so on. Now, this is an added resource that you get when you use quantum mechanical systems to store information, okay? So that is what is called as a qubit now. Instead of bit in case of a classical computer, in the quantum case, you call it qubit. So these qubits will store information, and one can manipulate the states of this electron in such a fashion that you get to do certain calculations using the principles of quantum mechanics, not classical mechanics. And there are a lot of proposals and algorithms which have been developed on paper which show that certain calculations can be done much faster way than what our classical computers can do.
Well, you can maybe that's the very peaks.
Yeah, you can create whatever superposition you want. 10%, 90%, 5%, 95%, whatever.
Basically, that is the speed with the chance.
Huh?
That is what? Whether you see the speed?
No. Probability is no. So when I look at the atom, say 1,000 times, if I have created a superposition, 50-50 superposition, 500 times I will see that the electron is in the lower state. 500 times I see it in the upper excited state. So this probabilistic nature of quantum mechanics is very counterintuitive to our classical understanding. So that kept puzzling people a lot. But although a lot of people debate about the foundational aspects of this quantum mechanics, but it works nevertheless. It has worked in all the system, it keeps on working. So there is no doubt that quantum mechanics works. So
This is we need one of the way to supply.
yeah, so I will, if I get time, I will tell you. So for instance, here,
Yeah.
forget about this side. So there is one, this is a state of some electron in some particular atom in the ground state and excited state. Now you can shine light which is of this exact frequency and change the population from in this and this. For example, if I keep shining the light, the population in this excited state keeps increasing and oscillating. Now if I shine light only for a certain amount of time, I can decide whether it's half the times here or half the times here, and so on. So that is how you manipulate the state. And same thing is with light, photons. Light can also be treated as particles called photons, and light has polarization, either vertical, horizontal, right circularly polarized or left circularly polarized. Those are also two quantum states of light, the polarization state. One can also manipulate that and use photons as qubits. So this I have said already. So the classical bit can either be in 1 or 0 state. But the quantum bit can be exist in either of the two states with certain proportion which you can control. So this is the principle of superposition. Now, one more thing that I said about infinite possibilities of this quantum bit being in the different states is this 0 and 1, right? So one can represent this 0 and 1. You take a sphere, ball, the poles of the sphere, you represent them as 1 and 0, and one arrow pointing to either 1 or 0. Now this arrow can point anywhere on the sphere if you move it. Now this the location of this arrow on the sphere anywhere is decided by the proportions of A and B, which means you have so many infinite possibilities of this arrow being located anywhere on the sphere. So this is what is the one of the important aspects of quantum mechanics that one uses for doing information processing. Another thing. So if I take a single qubit or a quantum mechanical system, which has, I represent its states by these arrows pointing up or down. Now, as I said, you can create some amount of A plus some amount of up, some amount of down. If you had two of these, then there are 4 possibilities, both pointing down, both pointing up, one of them pointing up or down. Now you can create superpositions of these combinations also, if you had 2 qubits, because you have this entanglement as a resource, right? Not only the superposition of 2 states of a single electron in those 2 orbits, but if you had more than one atom, you can also create their superpositions. So you have 8 possibilities for 2 of those systems when you combine them. Now, if you take 3 of them, for 3 you have 8 possibilities. Now imagine if you had 300 such qubits. The number of possibilities are more than the number of total atoms in the entire universe. So the amount of resource that's available when you choose a quantum mechanical system is just mind-boggling. So these are some of the things that attracts, I mean, there is a lot of investment going on across the world, putting money into quantum technologies. Even in India, the government has launched this national quantum mission, about 6,000 crores or so, over 6 years. And a lot of researchers are working on many things, including us. We are developing a quantum computer with ions in our lab here. So, just to give you a flavor of this, the dimensions of this fuzziness that I talked about, okay? You take a cricket ball, you calculate the fuzziness, which is given by what is called as a de Broglie wavelength. There is a formula. Planck's constant divided by the momentum of the particle. For a tennis ball, it's just too tiny to see. It's 10 to the power minus 34 meters. Okay, so it doesn't matter. In a classical world, quantum mechanics doesn't matter at all. Same thing, you take an atom, okay? At room temperature, the wavelength of the wavelength associated with an atom is about 8 nanometers. Now that's about 25 times larger than the size of the atom itself. So you go to smaller sizes, the wavelength keeps increasing. So this wave nature of these particles can be used to increase sensitivity of certain sensors. Like, how many of you heard about gravitational wave detectors, LIGO, Michelson interferometer? Okay. So in Michelson interferometer, people use light and build an interferometer where light waves interfere and create fringes, and when length changes, the fringes move. Imagine using atoms instead of light. If you use atoms instead of light, your sensitivity can increase by many fold. Now, one classic example of that is a electron microscope. See, with optical microscopes, when you use light, the sizes of objects that you can see are limited by the wavelength of light, which is about half a micrometer. So you cannot see objects which are smaller than half a micrometer. So if you want to see objects much smaller than that, you need some waves whose wavelength is much smaller, is smaller than the objects that you want to look at. For instance, you want to go into the nucleus and look at DNA. It is not possible to look with optical microscope, right? Then what people use is they use particles, high energy particles, where the associated de Broglie wavelength is small, and you scan these waves on the surface of these nuclei, and then you see the image. And what is used is electrons. Electrons which are accelerated to several tens of kilovolts of voltage. And yeah, one second, let me finish this sentence. And then you go to a source of light, light in quotes, whose wavelength is much smaller than this DNA, and then you image. So that is the application of wave particle duality. Please go ahead.
Take complicating the example, the need to be associated without reading.
Without?
You said the wavelength can be made smaller. How exactly is it done?
So you can, for example, in case of electrons in an electron microscope, you accelerate electrons and generate a beam of electrons, which is going very fast. You can change that acceleration by changing the voltage that is applied in what is called as an electron gun. There is an electron gun inside which generates a beam of electrons. You can change the velocity of them. By changing the velocity, you change the wavelength associated with the electrons. In case of atoms, you can slow them down or accelerate them to increase the wavelength or decrease the wavelength.
Sir, what is a qubit?
So I showed a picture of this atom, right? Hydrogen atom, for example. That electron can remain in different orbits, right? Can stay in different orbits. I can excite from one orbit to the other orbit. Now this electron is a qubit, for example, because it has, you can define two states where I want to excite it or de-excite it. If it stays in the lower orbit, I say it is 0. If it stays in the upper next higher orbit, I will say it 1. And I can create a superposition also. This entire atom is a qubit now.
So thank you.
Besides Microsoft succeeded in achieving the topology and qubit. So can you explain what is that?
Okay. Microsoft did not achieve a topological qubit, let me say that. They have done, they succeeded in one important step towards making a topological qubit. So, yeah, so you can read about it a lot on the internet. There are, in fact, you can also go and read about the editor's comments itself who accepted the paper in that Nature journal, okay? You can go and read that. There it's clearly mentioned what they have achieved and what they have not achieved. So it's not, they have not achieved a topological qubit yet. They have not demonstrated yet.
Like, what is an approach?
So, for instance, in this case, I that the electron will stay in either one orbit or the next orbit, right? Now the problem is with this quantum mechanical systems, when the electron stays in the higher orbit, it is not going to stay there forever. It will come back to lower orbit by emitting a photon. This is because of another very profound concept in physics called as vacuum fluctuations. Vacuum fluctuations means even if you take out everything from this room, there is energy in the room which is called as vacuum energy, which is basically electromagnetic radiation at all frequencies. Now there is some electromagnetic radiation of exactly the same energy which corresponds to the energy difference between this electron's excited state and the ground state. Now those waves, electromagnetic energy, is going to stimulate that electron, continuously keep bombarding it to go to the lower state. So this is spontaneous emission. Now this spontaneous emission, this phenomenon actually spoils the qubits, the nature of the qubits. I think I'm going to stop after this, so let me just take the questions. So this electron is going to come back to the ground state after some time. So that limits the time for which you can store quantum information. Now, in a topological qubit, you create certain states of these electrons in such a manner that it's a combined state of more than one electron. And it is like, for example, a circular current or something inside inside some planar structure. Now, these structures are created in such a manner that they are naturally protected from going from one qubit state to the other. So, in order to take them from one state to the other, it costs more energy, much more energy than what your perturbations, external perturbations are going to cause. So these qubits are called, the topology is that structure that you create. It could be a circle, it could be some knot, it could be some complicated knotty structure, whatever. So these are topological states. Now to go from one topological state to the other topological state, it costs a lot of energy. So that's why these topological qubits are naturally protected.
Right.
So I don't know the details of how they create that because I'm not from that field, but the general principle is that.
I guess.
Yeah.
Nice. You want to thank you.
Sir, I have one question here.
Sir, go. Excuse me.
Yeah.
So, an excited electron, it stays in the excited state, and how long it remains in this excited state? Does it depend on the energy level? And this time for which it remains in the excited state, is it in any way related to quantum mechanics, probability or?
Yes. So I showed a very simplified picture of these electrons, right, in different orbits. Now, in different orbits, there are certain properties of the electron like total angular momentum and so on. Now, this total angular momentum of the electron is dependent upon the spin of the electron, the orbital angular momentum of the electron, the spin of the nucleus, and so on. All this combined, they give a particular momentum value, total angular momentum value of the electron. Now, when an electron jumps from one orbit to the other and emits a photon, the photon carries momentum equal to the momentum difference, angular momentum difference of the two orbits. Now, if you go to a state such that, now in all this process, there are things like energy and momentum which have to be conserved simultaneously. So the energy difference has to match the energy of the photon. The angular momentum difference has to match the angular momentum of the photon that is emitted. Now, if you have taken an electron in such a state that if it jumps to another state, it is not going to conserve angular momentum, then it will remain there forever. It all depends on many complicated. So these are called as, for example, there are electric dipole allowed transitions, which are faster in the sense they decay faster. There are electric quadrupole transitions which decay much slower, so their lifetimes are in seconds. If they are dipole transition, the lifetimes are in nanoseconds. If they are in octopole transition, the lifetimes are in years. So it all depends on those factors. Yeah.
So,
Yeah.
could you please explain what a force of nature or the state is?
So light, as I said, energy is quantized. The basic, the starting point of all the quantum mechanical principles, right? So we said Planck's quantization principle of energy. Now, electromagnetic radiation is also quantized in the sense it is not emitted continuously, but it is emitted in packets. These packets are equal to Planck's constant multiplied by the frequency of that electromagnetic radiation. So this packet is the photon. The packets that are going, which are carrying that energy, are photons.
Thanks.
Yeah.
Class test.
Cool.
So I think the most important question of all, if students want to get into this field, how should they do it? What is the path to that?
Okay. So the path is a very standard path. The thing is, obviously, one needs to learn quantum mechanics, but in standard traditional pedagogical approach of physics is that there are after your 11th and 12th, you start with bachelor's in science or BTech in science or whatever in physics. Then then it starts building up, right? So you learn mathematical methods, you learn classical mechanics, you learn electromagnetic theory, you learn statistical mechanics. These are like pillars of physics. So you learn these foundational pillars, and then at some point after your BSc, MSc, when all these pillars are built, then there are many fields within physics. Depending upon your interests and all that, you get channeled into one of the fields. Now quantum technology is another field, but yeah, I mean, at that point you can decide to get into this. So, but the foundational principles have to be very clear. Only then you can start building on it and thinking about and then in that also there are many subfields. Quantum computing with different platforms, atoms, ions, superconducting qubits, photons, electrons. Each one is a subfield in physics itself. Like for example, with atoms and ions, it's about atomic physics, knowing atomic physics. With superconducting qubits, it's about knowing solid state physics and condensed matter physics. So these are all subfields. And then you finally specialize into focusing on doing only one particular.
It is all education.
Yeah.
Let's say even after the first guy didn't IISER Pune. So that how do we get a job at how the
Jobs, okay. Only in the recent times, the investments in this area are increasing a lot. So globally, even in India, there are a lot of companies, startups which are coming up, who are aiming to develop many devices, not only computer sensors, communication systems. So those are areas where there are opportunities that are opening up. And since there is a huge projection of how this market is going to increase, this industry is going to definitely keep increasing at a very rapid pace. So, yeah. So once there is a large industry base in this area, then there will be opportunities for the jobs in this particular area.
pathways through core sciences are not because
Electronics engineering, so in all these quantum technological devices, the core, which is the quantum core, is about 5 to 10%, but it is the hardest of it. Rest of the part is all standard classical engineering, electronics, mechanical, communication, all those software, all this comes in that 90%. So even if you don't do the physics part, you still have a lot of opportunities in the areas of these quantum technologies.